Hello students, in this lecture we will discuss about Colpitts oscillator. By now you have learned tuned collector oscillator and Hartley oscillator. And the Colpitts oscillator is very similar to the Hartley oscillator, and the only change is in the construction of the tank circuit. First we shall understand the circuit diagram. As normal case we have R2, R1 and R2 and RE which are used for the biasing of the circuit. Then instead of this RC resistor, you have here radio frequency choke or an inductance coil which actually chokes the radio frequency signals, or you can say it will actually give high impedance or offer high impedance to the alternating current high frequency signals, and this is very much required for the initiation of this oscillations. So this actually in a way it actually imposes a choking or actually impedance to the AC signal, so that actually it will keep the VCC safe. And in a way this actually reducing the or eliminating the AC signal flowing towards this or flowing through this resistor is very important for keeping the biasing such that you get oscillations very proper in the beginning of the oscillator circuit. So that is about the RFC. Then you have, as usual, you have a coupling capacitor which actually bypasses the AC signal which you really require in the oscillator. Then you have the tank circuit. And the tank circuit, as in the case of a Hartley oscillator, it is kept between the collector and the, you can say, the basically the base of the transistor. And so here it is taken out of the capacitor or the collector, and then you have the inductance coil and the capacitance. So as in the case of a tank circuit, always we have an L and C combination in parallel to each other. But in the case of an Hartley oscillator, you were actually taking a ground between, or you are tapping from the middle of the L or somewhere between the within the inductance coil L. But here what you do, the grounding is between the between the capacitors C1 and C2. So you have two capacitors C1 and C2 in series, and you are grounded in between. So basically you can say that so this is the peculiar feature in the case of a Colpitts oscillator. You have two capacitors instead of two inductance coil. You have two capacitors C1 and C2. Now another important thing which we have to understand here is basically this tank circuit or this produces oscillations as in the LC oscillators. But then when you produce oscillations, you know that capacitor will get charged, and the inductance capacitor electric field in the capacitance and the magnetic field in the produced in the inductance coil, they will change alternately they will transform its energy to one from the other, and because of that oscillations will be produced. Now how you get the 180-degree shift in the feedback signal? So that is actually one thing very important. Now you see, you give something or something is given into the input of this, and after amplification you get the phase reversed signal here, okay, which is amplified. But okay, then that will produce whatever it be, it will produce polarities in the inductance coil, and similarly capacitor will also get charged. So suppose first the capacitor here, this is positive, and suppose this is negative. It will basically depend upon the end of the inductance coil, if it is positive and it is negative. So capacitors will be charged accordingly, right? So now you see the capacitor voltage or the voltage developed across the capacitor C2, that is this voltage. The voltage between this two terminal and this terminal, that is actually given to the base of the transistor. So that voltage, when you take at the point, or you can say if I consider this point as A and this point as B, the voltages at the point A and the point B will be opposite in polarity. As you can see, here it is positive, here it is negative. When this becomes negative, this will be positive. So since the voltages at the points A and B are in opposite polarity, the voltage which you give back to the feedback through the feedback network, which we give to the base of the transistor, will be exactly out of phase with the output voltage, or out of phase with the voltage across the capacitor C1. So then when you so I can say that this voltage, when it passes or when it is given to the tank circuit, when you get it out of the C2 or when it is fed back to the base of the transistor, that will be again phase reversed. So now you see this signal which is coming out of the feedback tank circuit, or that's across the V2, that will be in phase with the previous input signal. So you can see it actually produces actually the feedback network here produces 180-degree phase shift from the output signal. Or thus you can get sustained oscillations in the case of a Colpitts oscillator. Okay, so this is how it works. Now we have to think about the beta. Okay, and you can see the feedback fraction beta that depends upon the feedback network, and this feedback voltage, output voltage, is basically the voltage across C2, and input voltage is the voltage across C1. So that is actually, I can say the voltage is actually voltage across C1, and this is voltage across C2, and this is voltage across C1. And the voltages across these two, voltage across a capacitor is inversely proportional to its capacitance value. So I can say this beta is inversely proportional to beta is inversely proportional to C2, and it is directly proportional to C1. This VC2 is inversely proportional to C2. So I can that say this C2 comes here and this C1 comes here, and that is how this beta becomes dependent upon C1 by C2. So this is something which is very important. And another thing we have to keep in mind is that we have, for having sustained oscillation as per Barkhausen's criteria, we have to see that A beta value should be greater than right, or equal to 1, right. So when I say that, I can say that this AV value, this is AV, this AV value should be greater than or equal to 1 by beta, right. And this, you have seen that this 1 by beta, beta is C1 by C2. What is 1 by beta? That is C2 divided by C1. Okay, so for the AV value to be greater than or equal to 1, or to satisfy the Barkhausen criteria, and we said that for oscillations to start, for sure you have to have a beta value greater than 1. Then only you can have high oscillations in the beginning. So then you can get back the A beta to 1. But initially, to start the oscillation, the AV value should be greater than or greater than C2 by C1. So you can make sure that when you design the tank circuit, you keep the value of C2 greater than C1. Now about the frequency of the oscillations produced. As in the case of an LC oscillator, frequency is 1 by 2 pi root of LC. And what is LC? L is this L coil, L inductance of this coil. And what is this C? C is actually the effective capacitance. You as can see, two capacitors are connected in series. So the effective capacitance is equal to, the effective capacitance is equal to C1, C2 divided by C1 plus C2. Okay, so that is the effective capacitance value. So that so you can, depending upon if you design the value of L and C accordingly, then you can get frequency of oscillations according to our desire. And this Colpitts oscillator normally works between a frequency range of 1 megahertz to around 500 megahertz. So this is how a Colpitts oscillator works, and these are the basic working and as well as the mathematics associated with this or the frequency and the design of the capacitor and the AV value, in consideration of the AV value, and the frequency is frequency of the oscillator is discussed here. So thank you very much.